how we calculate pH from concentration of H plus or POH from concentration of hydroxide. On your Greg sheet, you're given this equation and this one. So if you have your concentration of H plus, you negative log it, you get the pH. However, you're not told how to go the other way. So if you're given the pH, you have to be able to derive the equation to figure out how to calculate the H plus. So let's get the H plus alone from here and see what the other equation is. First, I'm going to do the opposite that's being done. So I'm going to multiply both sides by -1. So I have negative pH equals the log of H plus. And then I want to undo that log, so I'm going to anti-log, which is, on your calculator, 10 to the. So 10 to the negative pH is equal to, instead of undoing the log, so the log's no longer there, it's just H plus. So the concentration of H plus is equal to 10 to the negative pH. Same thing with the POH. Multiply both sides by -1. Anti-log both sides to get rid of this log, and I'm left with the concentration of hydroxide is anti-log of this negative pH, so 10 to the negative POH. Okay, so now there's 4 very helpful equations for us. Your Greg sheet also has POH plus pH equals 14, and the concentration of H plus times the concentration of hydroxide equals 1 times 10 to the negative 14th. You don't have to memorize these two either, but you do have to remember they're there so you can use them. And the reason they work is this is a K constant. This is saying if you have water, water always has this equilibrium of H plus ion, or I could have had 2 waters and I'd make hydronium. And, oops, here, I'm going to write this as a normal person would, and have water, which is a liquid, is in equilibrium with H plus and hydroxide. So the K expression for that is, I leave the liquid out, K is equal to concentration of H plus times concentration of the hydroxide, and that happens to equal 1 times 10 to the negative 14th. So if you get extra H pluses or extra hydroxides so that when you plug in their concentrations it's larger than this, it means there's too many of them floating around in solution. They're going to find each other, they're going to come together, and they're going to make water. So this is the maximum amount that these concentrations can equal when they're multiplied together. So let's calculate. For the first one I look and I see, I'm going to find the pH of everything. For the first one I see I've got hydrochloric acid, that's one of my 8 strong acids. Strong acids dissociate 100%. So if I have 1 times 10 to the negative 5th molar HCl, I really have 1 times 10 to the negative 5th molar H plus. And I remember, or I just look on the Greg sheet, pH is equal to the negative log of the concentration of the H plus, which was 1 times 10 to the negative 5th. So if you plug that in, you'll get that pH equals 5. Make sure you try it so you know how to plug these in. Then for the next one, I have 1 times 10 to the negative 5th molar hydroxide, sodium hydroxide. And look at this, I've got an alkaline metal, so it's soluble, and it contains one of those 3 things we said, hydroxide, oxide, amide. It's a strong base. So if it's 1 to the 5th molar sodium hydroxide, it's also 1 to the 5th molar hydroxide. Okay, so POH is equal to the negative log of the concentration of hydroxide. So that's 1 times 10 to the negative 5th. So the POH is equal to 5. We also saw on the last page, or on your Greg sheet, that pH plus POH is always equal to 14. So if I subtract POH from both sides, I can say pH is equal to 14 minus POH. In this case, that's 5. 14 minus 5 is 9. So pH for this one is 9. Now, we have that different equation where we have to start with the pH, find out what the concentration of the H plus is. So I know that pH equals the negative log of the concentration of H plus. So to rearrange that, I multiply both sides by a negative 1. I anti-log both sides. So 10 to the negative pH is equal to the concentration of H plus. And here, I've got my pH is 3.5. So 10 to the negative 3.5 is my concentration of H plus, and when I plug that in, I get 3 times 10 to the negative 4. Okay, and this has 1 sig fig. pH only has sig figs after the decimal, so 1 sig fig, 1 sig fig. for POH, if the POH is 2.5, and I know that from here, 14 minus POH gives me the pH, then 14 minus 2.5 gives me 11.5. That's my pH. Okay, so that's the pH. And from here, I can see 10 to the negative pH gives me the concentration of H+. So I'll go 10 to the negative 11.5. I'll plug that in, and I'll get that that one was 3 times 10 to the negative 12 when I rounded to 1 sig fig, because there's only one number after the decimal, so that has 1 sig fig. Okay. Let's look at a few more. I have, what is the pH of a 0.05 molar hydrobromic acid solution? So it's one of my 8 strong acids that I memorized, so I know it's going to dissociate 100%. So if it's 0.05 molar hydrobromic acid, it's also 0.05 molar H+. Okay, so pH is the negative log of the concentration of H+ from the grig sheet. So I type that in, and I'll find out that the pH is 1.30. That has 2 sig figs, that has 2 sig figs. For this one, this is a little different. Potassium oxide, I've got an alkali, and I have oxide. So it's soluble, and as the oxide, it's a strong base. So when I put K2O in water, the alkali metal is always soluble, so I have these 2 K+ ions, they're floating around, they don't really do anything. And I'm leaving behind an oxide, O2-. O2- can't be in the presence of water. It's too negative, it's going to be attracted to the H+, it's going to take an H+ off of the water. So when O2- grabs an H+, it becomes OH-. It's also, if it's losing an H+ from the water, this water is losing an H+, that water is going to become hydroxide. So what happens, you can see there's 2 Ks, there's 2 Os, there's 2 H's. So it's balanced. If I have 1 mole of K2O, I actually have 2 moles of hydroxide. So it's 0.02 molar K2O, it's 0.04 molar hydroxide. So I know the POH will be the negative log of this, negative log 0.04. I type that in, and I can see the POH is going to be 1.3979. And again, I know POH and pH add up to 14, so 14 minus the POH gives me the pH, and the pH is going to be 12.60. That's 2 sig figs. This had 2 sig figs. So for the last one, I have a solution as a concentration of hydroxide of 1.5 to the negative third. So POH is just the negative log of the concentration of the hydroxide. So I just type that in, negative log, and I'm going to get a POH of 2.839. So that's the POH, and I know 14 minus my POH will give me my pH. 14 minus POH equals pH. So I just go 14 minus that, and I will get 11.18 will be my pH. There's 2 sig figs here, that has 2 sig figs. So last 2 problems. I have 0.36 grams of lithium hydroxide are dissolved in 250 milliliters of water. I'm looking for the pH. So since I'm given this, I'm going to find the POH first, which means I need the concentration of hydroxide. So 0.36 grams of lithium hydroxide. I'm going to turn the grams into moles. And I can see I've got 23.9489 grams of lithium hydroxide is 1 mole of lithium hydroxide. So that's 0.01503 moles of LiOH. And since it's a strong base, it has this alkali metal and hydroxide, I know it'll dissolve 100%. So if there's this many moles, there's really that many moles of hydroxide floating around. So let's get the molarity of this hydroxide. It's going to be the moles divided by the liters. So 0.01503 moles of hydroxide in 0.25 liters. That's 250 milliliters divided by 1,000. So the molarity is going to be 0.060128. It's the molarity of the hydroxide. So the POH is going to be the negative log of the concentration of OH that we just solved for. So POH is a negative log of that, the 0.060128. And when you type that in, you'll find out that the POH is equal to 1.22. And pH plus POH add up to 14. pH is going to be 12.78, because pH plus POH will add up to 14. For the last one, I have 2 milliliters of hydrochloric acid are diluted to 1.5 liters. I want to know what the new molarity is of H+, and then I can find out what the pH is. This is a strong acid, so if I have HCl, really, I have H+. Okay. So I want to find out how many moles are in 2 milliliters of 2 molar HCl, and then I'll divide that by 1.5 liters to get the new molarity. So 2 milliliters, there's 1,000 milliliters for every 1 liter, and for this solution, for every liter, there's 2 moles of that H+. That tells me 2 divided by 1,000 times the 4, I'm going to have 0.004 moles of H+. Oops, H+. And the molarity of the H+ will be that 0.004 divided by the liter. So moles per liter. That's liters, that's moles. The moles per liter is going to be 0.026. So that's the concentration of the H+, that's the moles of H+ per liter. So I know the pH is going to be the negative log of the concentration of the H+, so 0.0026. So I'll type that in, and my pH ends up being about 1 sig fig. pH ends up being 2.6.